Hello everyone, my name is Jonielle McDonnough and our group is the Wearable COPD Electronic Stethoscope, and this is collaboration with the College of Nursing under Dr. Atelier. So COPD stands for Chronic Obstructive Pulmonary Diseases. And in this world, in the medical field, there's a lot of devices for the heart, and in order to detect the frequencies over a period of time and whatnot. So just to give you guys a little statistics, in 2016, COPD was the fourth leading cause of deaths. And in 2018, it jumped to the third leading cause. That's crazy. And we want to do something to bring down those numbers. So we are detecting abnormal sounds specifically for COPD patients in an electronic stethoscope, and like having it flagged, and then also being able to give that information to the doctor. So imagine having a malfunctioning device, and as soon as you bring it to the shop, the device starts to work perfectly fine. So there's that similar frustration that doctors experience with their patients. So patients come into the doctor's office and claiming that they have that the way that they're breathing and the way that they're breathing is abnormal and it's causing them some pain and some type of discomfort. So the doctor analyzes it, and they're not seeing anything that could be of question. So there's that frustration that comes back up again. So with that being said, our purpose is to develop a more sensitive device that can detect the abnormal breath sounds from the lung and send that information to the doctor to analyze and discuss with the patient. Also, another statistic that's really interesting is that women are 37% more likely to have COPD than men. And in hospitalizations for COPD in Florida from 2012 to 2017 was between 56,000 and 69,000. And in ER visits for COPD in Florida from 2012 to 2017 was 141,000 to 163,000. Yeah, 163,000. Especially with this pandemic, with COVID-19, I bet that's even more.
For our methods, we use two main methods. We use spectrogram, which is a visual representation of the spectrum of frequencies. And we also use Fourier transformation. It's to decompose an image to sine and cosine waves in frequency domain. We're using spectrogram and Fourier transformation because they will help with identifying with how the lung sounds behave. From there, we can identify COPD sounds from patients. We are coding the Raspberry Pi via Python to store the patient's audio information. And we are also using Audacity and to get a better understanding of the sound and for playback purposes, because it's a user-friendly interface. We needed to verify our Python code by using MATLAB and comparing our results so we know what we are doing. We are also talking about how our product looks, and my friend Jeremy made a video about how the design process took through.
So here we have our 3D design for our electronic stethoscope. I first want to give credit to Nick Owens from GrabCAD Community, who actually designed the screen plus the Raspberry Pi together in one package for us to use. So I would first like to start off with the head of the stethoscope, our bell. The reason why it's small compared to a standard one is that we researched that the smaller the bell, the lower frequency it can gather. And so that's why it's small and concise into this form. And then we decided to use the same diameter of the tubing of the stethoscope as the standard one, so it can collect enough information like the standard one. And we want to make it short so that it wouldn't be an obstruction to the patient, but long enough so that it can be flexible so that it can go around any patient's chest area. And then we have our casing. So our casing is a waterproof casing made of a plastic material. So we want to make sure that in case the patient would be in an environment like rain in Florida, or they by mistake got into a shower with it, that it wouldn't damage any of the components inside of the stethoscope for us. And then we have our circuit design right down here. So the circuit design has the microphone chip, has the recording, and all the other components that we need as a so far, like the potentiometer and resistors and stuff that we need and stuff to actually get the gain to amplify the circuitry itself. And then we have the Raspberry Pi that we're actually using for the Wi-Fi and the storage capabilities from it. And we'll also be connecting it for our power supply as well, and a fan, but there was actually no space to actually create the fan right now, but there will be one. I actually have another design here on the side and stuff to display what the fan would look like. But later on, it would be attached to the Raspberry Pi itself around this area so that it can cool the whole system. And then the screen itself is created basically to make it user-friendly for the physician or the IT department in case they need to fix any errors on the device itself. It makes it real easy for an IT department to actually go to the patient's home and fix or update any issues that's having by using this touch screen itself. So we want to make it as easy and user-friendly as possible and stuff for the patient and for the doctors themselves to use this device on at least everyday situation for 12 hours. So this is our design. Thank you very much.
For the data analysis, for Dr. A, we have an older prototype that we have tested before to see the frequency range. So through that, we created an advanced prototype with the multi-functions, with the multi-potentiometer resistors and capacitors to amplify and to have a better sensitivity for a lower frequency microphone by adding a microphone that attached to our dual op-amp to give us a better range of a frequency and also for hearing samples. So when we by powering up with the Arduino, we only use Arduino to power up our circuits, but for our test we had made two samples tests in Audacity. First by using the Dr. A sample and our prototype, and you could see the figure 3 and figure 4. This is our sample or the new prototype that we made with the application. And by coding also we developed also a frequency running frequency simulator by using MATLAB and Python to match them and to see to detect the COPD sounds. For our result, since we didn't have our patients, we used this prototype in a smoker, so we could test our frequency range and to see how better sounds we could get. So we found out in the new stethoscope that we built from Dr. A stethoscope is the better in more like it's better, as you could see in figure 5. We have a low frequency and the sounds of the frequency is really small and it's really hard to indicate the sound of it. But in the figure 6, you could see it's much better results for our product, and it's because it's less noise and it's picking up like the sound of the lungs better for the wheezing and the crackling. And also as figure 7, to have another process and a better process of our result when we get it, as to send these data that based and restored in the circuit to an email to the doctor.
So our final design was pretty successful. It detects a frequency of interest, stores the data, and notifies the physician via email. So this project challenged us in the fact that we had to use our knowledge from previous classes such as Lab 1 and also learn other things such as pattern matching and masking. We use a lot of MATLAB in order to verify our code in Python, since we're using a Raspberry Pi. And due to our knowledge in MATLAB, we had more knowledge in MATLAB, so we knew that that information would be correct. And with that, I go on to say that even with COVID-19 happening right now, there's two things that affected us. We weren't able to test on COPD patients as scheduled, and some parts weren't able to come in time. So when we were ordering some parts, they said, oh, they will come in May, and that's after this due date that is coming up to submit our project. So with that, we realized we just had to do other things and just improvise, basically. And what better way to improvise than as being an engineer? So from the results of Dr. Al Hassan's stethoscope and our stethoscope, we saw the amplification from our circuit using the dual op amps. And it obviously shows from figure 5 and 6 that we have the more sensitive electronic stethoscope. And it also has less noise from the body and the environment. So that's very good due to the fact that this is a wearable device. And as they walk around throughout the day, there will be noises from the environment and also their body that would want to affect the signal. So yeah, so due to COVID-19, we couldn't test on those COPD patients. So we tested on normal patients and also a smoker too, since we have one handy to us. And so we just modified the code in order to accommodate that frequency. So the frequency of interest can be replaced at any time in order to accommodate the COPD patients in the future.
So like previously discussed, our device allows the physician to monitor COPD diagnosed and possible COPD patients remotely. We made sure that with the Raspberry Pi's functions, we were able to store our data in real-time situation and email the physician with that data and the patient's information as well. We want to make sure that it was simple enough for the patient not to have to do anything and is just relied upon its own devices and the doctor's analysis as well. So we succeeded in developing a more sensitive device, as you can see in the previous figures that we discussed earlier. And all we want to do is just to make sure that the COPD patients are taken care of. If we can save one at a time, that's gonna be the best thing for this device. Thank you.
We would like to acknowledge Dr. Hoff, Dr. Attili Ham, Alex Alton, and Nasser Aboerjaib. And disclaimer.
So there's a disclaimer. We are not the professional doctors, only the engineers, and rely on the doctors to confirm the diagnosis after analysis of our data.
Now we're transitioning to our final product to show you how it works. Project. So we're using the Arduino just as a power source, as you can see, but we're using this board so we can collect data from it. So we can start using it. So I have everything connected to the aux cord from the output of our microphone. So transport. So now I would stop the recording, pause it, and I would start playing it. and I can listen to it via the headphone jack. Here. Perfect. Yep, this is our project. So this is the test we took, and we did it on the computer so you can listen to it without headphones.